zeichnen. Okay. Was ist denn jetzt wieder los? Ich sehe, das ist ein Fehler. Moment mal, ich muss noch mal probieren. Ich habe vielleicht auf den falschen Ding geklickt. Jetzt. Gut. Okay. Jetzt. Können Sie mich hören? Good. Okay. Let's go on. Corollary. So it's about what happens with the tensor product when the modules are free. So let's assume M is free. If M is a free A module, so remember free means the module has a basis. So let's say the basis is VI indexed by this index set, not necessarily finite. Then any element of the tensor product, okay, can be uniquely written. As, okay, it's a sum over I and I. Of course, it's a finite sum. This I means written. Okay, and here on the left-hand side, I can put a basis element, tensor some element ui in n, okay? With the ui are in n. And this is unique. Of course, almost all ui are 0. Okay, so you have this uniqueness. Okay, very good. And 2, if M and N are both free, if M is free with basis BI and N is free with basis, and this I denote WJ, then M times N is free with basis. The basis is just obtained by the tensor products of the base vector. So BI tensor WJ. And of course they run, okay, over the pairs. So, okay. So in particular, if over a field, if my ring, my base ring is a field, and M and N are finite dimensional vector spaces, finite dimensional K spaces, then my tensor product, of course, it's free, it's a vector space, but the dimension of the tensor product is the product of the dimensions. Because the dimension of M is the cardinality of the index sets I, the one of N is cardinality of J, and so that's it. Okay. So it makes a lot of sense. You form the product, the tensor product, the dimension is multiplicative. Okay, of course I have to prove this, or is there a question? No, okay, let's prove it. Okay, proof of 1. So M is supposed to be free. So up to isomorphism, so without loss of generality, I can assume that M actually has this concrete form. It's this direct sum. Okay, so you remember what this was, okay? It's a subset of the Cartesian product, but only finitely many of the components are non-zero with component-wise operations. So whose elements are like families or sequences, families, where AI is in A, all but finitely many AI are zero. Okay, so then, okay, I can also write, okay, I can write M as in this way. Okay, I write this a direct sum of copies of A. This is okay. This is the same as the other thing. And by, okay, now I want to put to this, okay. Let's put the star here to this relation. This relation I'm going to use now. It expresses in a way distributivity of the tensor product over direct sum. And it's also true if, I mean, if the number of summands is infinite, it doesn't matter. Okay, always true. So I use this by, okay, by the star we get, okay, now one line of formula M tensor N. Okay, first instead of M, I write this tensor N, and now comes this star thing, canonical isomorphic to the direct sum of the tensor products. Okay, but I know A tensor N is canonically isomorphic to N. So this is sum N. And this was the proposition. Okay, it was a proposition, doesn't have a number. The one that I proved first. Okay. So I showed, yeah, what did I show? I didn't show M tensor N is free, but how about this uniqueness of the representation? So then we have to see actually what this isomorphism between and here actually does. Okay. So here, so on the left hand, what do I do? What do I want to say? Okay, so if I have a family Ni as an element of this sum, so this corresponds to this. Now this maybe takes a little bit of thinking. Okay, where the EI is just a canonical basis. Sorry. Where EI is the canonical basis of this. So think of, I mean, think of I being finite, okay? So then this is the standard basis where at the position I, you have a 1 and 0 elsewhere. This is our standard basis. Okay, so but now, why is this? Let's see. Do we have to prove anything here? So the, I mean, the claim is this, that here on this module, we have these elements, okay? And the claim is if I take such an element and I map it here, what I will get is this. Okay, now let's stare at it. Did anything happen? I mean, no one has to check it. Okay, you see, maybe I just write one step. You see, for instance, here I have, right. So what I know, the I tensor Ni in the ith copy of this guy will map here to Ni, for instance. You see? Actually, I don't feel like writing it down formally. It's but you see, if you have here, you have the E, maybe I shouldn't say I because it's a running index, J, okay? I have, maybe I can write, maybe in another color. Now you can also ask me. So if I have like the EJ here. So what is it? You go into the components. If J is different from I, you have component 0. If J equals I, you have EI, okay? No, sorry, you have 1. You have 1, right? So you see, now if you look, this EJ, okay, tensor N, okay. Right, so actually yeah. Okay, let me suggest that you maybe check yourself this, and then if you have a problem, you ask me, but it's a straightforward thing. I mean, you just, right. How would I prove? Okay, how would I prove? Say I want to prove that this corresponds to this. But you see, I have a linear map. So actually it's enough. Actually, it's enough to say fix I, okay, and then you look at this element. Okay, and you show where it goes to, and then you show it goes to this family where everywhere is 0 except at the position I. So okay, I want to write this family this way, you understand, okay? And then we just have to check it. So the point is, right, at the position I, the EI gets 1, and then we are here. I mean, it's really trivial. Okay. Please verify it yourself. But right. So, but now we have, I claim we have shown the statement. What do you want to show? Every element of M tensor I, okay, every element here can be uniquely written. Now our basis VI is now the standard basis, is the EI, okay? And I have written every element, I have to show every element can be written uniquely this way. And this is what I have. If I have such an element, I know it corresponds to this family. Yeah, if you have an element here, it uniquely determines this family Ni. So it uniquely determines this. So it's a one-to-one thing. Okay. I suggest take for I maybe a finite set, okay? And then write down exactly what these isomorphisms are, and then you will see that it holds. It will be very clear. Okay, let me go on. Here a difficulty is that I can be infinite and I cannot write it maybe so nicely. So part 2, if M and N are free, I can assume, okay, let's say without loss of generality, M is this, N is this, okay? And then by part 1, we get M tensor N is isomorphic to direct sum over the N's over here. So I used part 1 and then I use it again. I use it twice. And here is A. But this is canonically isomorphic to the direct sum of the A's over all pairs. Okay, and then I showed it's free. Okay. Mhm. So maybe one should say that this notion of tensor product is not even over for vector spaces. So even if the ring is a field, it takes time to get used to. Okay, so I suggest if you want to really understand this, first, okay, take for I a finite set, and then if you want, first take for A a field. Okay, and then check it. Okay, do. So, so what can we do now with this? So now here comes an example showing that the tensor product is really a flexible way to relate different rings. So maybe we can call this application. I mean, it's maybe not a true application. It's not an application in the TU sense. Application to polynomial rings. So okay, let's assume I have a ring homomorphism from A to B. So ring morphism. X is a variable or an indeterminate. Okay, and this induces ring morphism from the polynomial ring in the variable x over A to Bx. I also denote it by F. Okay, they are both F. Okay, induces morphism of polynomial rings. So what I'm interested here is the change of the scalars, if you want. So here I have polynomials in the ring where the coefficients are in A, here the coefficients are in B. So if I have this map from A to B, I can map polynomials with coefficients in A to polynomials in coefficients in B. Okay, so this F could be, for instance, inclusion, but it can be also something else. Okay, now let's see, what does it have to do with the tensor product? Now I view B as an A module in the following way. How can I view B as an A module? Oh, well, the operation is this. So here is my scalar A, multiplication, I denote by dot with B, will be defined as follows. The only, what can I do? I map A, I get f of A, I have an element of the ring B, which I multiply with B. So this is the definition. It's immediately checked. This turns B into an A module. Okay. Now consider the following A linear map. So okay, here I have now a tensor product. Let me put here the index A for the sake of clarity. So this is to be interpreted as tensor product of A modules. B is an A module, I just defined it. AX is also an A module, right? It's clear, it's an A module. So I can form this tensor product. The question is, what is this tensor product? And I will show this is actually B of X. And I will show it first by defining this map. So I have an A linear map, which is well defined and sends, okay, a generator P tensor, and here I can, let's say P. Okay, so I will write what it is. So what should I write here? Okay, any guess? What do I mean, there's not much I can do. I mean, P lives here. So I map it. I get f of P. And this I can multiply P, sorry. F of P. And this I can multiply with P. Okay. So I have to check that this map is well defined, but it's the usual story with the universal property, okay? Usually blah, blah, blah. It's a well-defined A linear map, okay? That's exactly one with this property. So maybe I should say, okay, what I should say, maybe I haven't said already. So B is an A module. AX is an A module, but BX should also be viewed. This should also be viewed as an A module. Maybe I should write this. Then viewing left and right side as, aha, okay. No, sorry. I want to say something else. What I want to say is this guy is also a B module, okay? And it's possible to view this guy also as a B module. And then this map here is bilinear. So let's write this and check it. So when viewing left and right side as B modules, I say in the obvious way, there is only one way to see this. In the obvious way, then above map is also be linear. So maybe okay, I have to check the obvious way. Maybe it's not so completely obvious. That side, left, okay, left-hand side. Let me define what is the B module structure on this guy. How would I multiply with B? Okay, this is this. I say what happens on the generator. So B tensor P, sorry. So this is an element. This is an element of my tensor product. Now I define what is it, does it mean to multiply with an element B prime of B? This is should be this. I multiply the B's. Okay, this is the multiplication in the ring B, tensor P. Again, it's clear, hopefully. This definition only makes sense because of universal property, okay? Right, it's always not every element is of this form. So even for writing this, you need universal property. Then you define this map, this scalar multiplication, which turns this object into a B module. Okay, and then, some properties need to be checked, but it's trivial. And okay, right. And that the map is bilinear, this is also by definition. So I suggest if you want to understand this, you have to check every step yourself. There's a lot of little steps which are all trivial, but in the sum, okay, it's maybe, yeah, takes some time. But the statement is now that this is an isomorphism. So the claim, this requires a little bit of work. The map, okay, the map above map, maybe the above map is an isomorphism. Okay, as you can say isomorphism of A module, isomorphism of B module, doesn't matter. It's both. Okay, and the proof, the map we have. So the point is, why is it an isomorphism? And now we can use, in order to do this proposition here that we showed, where is it? Or this corollary, where it was this. Now we knew, okay, we use this corollary. Because we are now in a good situation, because one of the two guys here is free, namely this. This is a free module. The polynomial ring as an A module is free. Okay, so this allows me to do this easily. So AX has the A basis consisting of the monomials, x to the I is a natural number. Because yeah, every polynomial can be uniquely written as an A-linear combination of the monomials. That's how they are defined. So by the corollary, part 1, every element of B tensor AX can be uniquely written as a sum. And what I have, now it's on the right-hand side, it doesn't matter. Here is the basis. In the corollary, it was written on the left-hand side. Now I write it on the right-hand side, it doesn't matter. And here is an element of the ring B. BIB. Okay, and of course, BI equals 0, except for finitely many I, except for finitely many I. You see? Okay. So thus, our map. Now let's see our map here. What does it do? I mean, this element, where does it go to? Okay, the map maps to this. That's how it is defined. This is therefore bijective. It's a bijective map. Okay. So if I have a bijective map, I have an inverse, and it's immediate that this inverse is a module homomorphism. A module, B module, it doesn't matter. Okay. Okay, so are there questions on that?
I think you wanted to write metronymous as an index set in the last line.
In the last claim, I wanted to.
The last line.
The last line. What did I? Can you repeat? I didn't.
And natural numbers as index sets.
Ah, yes. Of course. Thank you. You are perfectly right. Let me see if it's also in my notes. No, in my notes is nothing. Good. Sometimes it's not good to write too much. Okay. So this process is called scalar extension. But what could, if I had time, but I'm running out of time, I'm afraid I will not go into it. But this is called scalar extension. You have an A module. You have such a ring homomorphism from A to B. You can turn your A module into a B module in a canonical way by doing exactly what we have done in this special case of AX to BX. So people would say BX is the scalar extension of AX. Okay. Right. And this is actually useful to know this. So right, maybe later on we will see how useful it is. Okay, if I have still time, I'll wait a little bit. The last, okay, I don't have much time, but maybe let me write it. So because we were interrupted, and so maybe let me do this example, at least put the statement. It's about the, okay, let's see. Say if you want to understand what is the tensor module, the tensor product of what? Of modules over the integers. So modules over the integers are abelian groups. Let's say finitely generated. Right. So there is a theorem, I don't know whether you know it. Every finitely generated Z module is really this of this form. You have a Z to the N, and then you have a sum. Okay, you get it by a direct sum of these components. This and this. Okay, will not be important. But this module here has torsion. So if you want to understand the tensor product, we have to understand what does it do with these objects. And that's what I want to explain in this example. I have two integers, and D is the GCD of M and N. So I remove this here. Okay, now, okay, I'm short of time, so will not ask you what it will be. So the question is, what is this? Okay, I can put that if you want. What is this tensor product? Okay. And this thing, I mean, it can even be 0. And the statement is, this is given by this, the modulo, and here you put the GCD. So in a way, this is maybe the most complicated way to explain what is the GCD of two integers. You can explain it in terms of the tensor product. The statement is, we have the, okay, we have the Z linear isomorphism. Okay, it's not that there is one, we can say what it is. Okay, it will map X to, okay, how can I write it? X times 1 tensor 1. Okay, one has to think that it makes sense. I mean, the proof will show that it is well defined. I can also write it this way, or I can write it this way. Okay, so the proof will show this is well defined. Okay. I think I should stop here because I'm over time. Let me maybe stop the recording.